All right, this is my lesson for 6.10b. And essentially, it is the same standard as we've been dealing with, except today we are going to discuss a new type of growth model, and it's called the logistic growth model. Okay, so let's talk about how this applies to real life. So never ending exponential growth, which we have modeled in this unit and have graphed and have solved, is often a very unrealistic model for many systems, as there are other factors that are involved. For example, availability of food or predators or some finite population, okay, that will limit the growth in a real world. So the whole point of these models is we're trying to develop functions that we can predict what's happening in the future, for example. So we can't grow exponentially forever in certain situations. And here's an example. So for instance, when smartphones first came out, the number being sold each year was increased roughly exponentially. However, that exponential growth is no longer an appropriate model for smartphone sales, because the more the population purchases the smartphones, it will no longer follow an exponential growth. So in other words, exponential growth is no longer an appropriate model, because as a large percentage of the population of the earth now already have smartphones. So sales are now much more affected by replacement of an old or damaged smartphone than by rapid adoption of a smartphone by new users. Okay, so it is a perfect example for what we call the logistic growth model. This logistic growth model is a function. So we have the model is y, the output in some future date is equal to this value L divided by 1 plus b times e to the negative k times t. So L is a constant, B is a constant, K is a constant, and T is our variable, okay, such as X, for example. This logistic growth model deals with these types of scenarios. They slow the growth rate when the system approaches the maximum capacity of the system. In this model, L is this carrying capacity. It is the point the maximum amount, okay, that we can get to. So the inflection point is a point in which the growth function starts to slow down. So until I meet the inflection point, my growth is speeding up. And then once I hit my inflection point, my growth starts to slow down. And that inflection point is essentially half the value of this carrying capacity, half the value of L. So you can notice here on this graph that when X equals T, the time at which, at T, the time T at some point, my Y value will be half of the carrying load, half of the L value. So this is where this inflection point will be, okay? Okay, again, this is going to approach some maximum amount, and this is considered a horizontal asymptote. One way we can find where that is located is we can actually determine the end behavior of this function as T reaches an infinity. Okay, so let's take a look at how we can use this logistic growth model in certain situations. So we have the number of mice on a large tropical island that can be modeled by a logistic growth function, and it's given there, where T is the number of months since a biologist noticed the colonization of the island by some mice. So we're going to essentially have a situation where the population of mice will grow exponentially, but eventually it's going to slow down because maybe there's not enough food source for the mice to continue to grow at that rate. Okay, so let's learn how to actually graph this function on our calculator. So we are going to actually take this function for the number of mice, and we're going to enter that into our calculator under y equals. So we will go and hit y equals. And let me go get my calculator, and I will see that I will plug in 2000 okay, divided by, and then I will put in parentheses that 1 plus 20 times e to the minus 0.1. And instead of t, we're going to use x. And that will be that key that is xt theta or n, and that will enter your x for you. Now, one thing I will point out is that you want to make sure your plots on the top are off. We have been using our stat plots quite a bit, so make sure that your plots are off so that this works fine for you. Now, once we've entered that equation into our y equals, we need to adjust our window so that when we want to go and look at the graph, that we can actually see the graph. The one thing that is easy to kind of see is this maximum value that y is going to reach, which will be our L in our equation, and that's where the 2000 comes from. And the scale is just how many how much per tick mark we want to see, so we can make an educated guess on that. But again, the 2000 is something that we should be able to determine from our equation that was given to us. We a lot of times have to actually use iteration to find out what our x values are going to need to be. And in this case, we can have minimum of 0, maximum of 100, and the scale is 10. But you're going to have to kind of play with that to kind of see where that window is going to need to be set so you can actually see that. And there's our actual graph and what it looks like. And in the beginning part, we have an exponential growth essentially, and then we have at some inflection point, we're going to actually, which will be at half of that 2000. So that's probably going to be at around 1,000. And then we will start to slow down. My rate of growth of these mice will start to slow down. And so what has the question asked? It says to describe its shape in context of this problem. So let's describe this. We will say the population of mice where on this tropical island initially grows exponentially. The growth eventually will peak. So the amount that it grows will eventually peak. Eventually will peak and start to slow down. Okay, now as that population reaches, actually more like approaches or gets near, approaches 2,000, then what happens to the grade? 2,000 mice, the rate, the growth rate gets very small, right? Essentially gets almost next to 0. Okay, there you go. There's the description. So we've described the first part. So the population of the mice on the tropical island initially grows exponentially. Then it will reach a peak. The peak growth rate occurs at that inflection point, and then it will start to slow down. And as it approaches that maximum, which is 2,000 mice, the growth rate will get very, very small. What is the horizontal asymptote for this function? And what does it mean in context? How do you find the horizontal asymptote of this function? You basically need to determine where this function approaches as x in this equation goes to infinity, okay, or t in this situation. So what happens as t goes to infinity, as the time goes to infinity, we have e to the minus infinity, which will become 1 over e to the infinity. And so that approaches some very small number, which is essentially 0. So this portion of the equation will approach 0. And then I will add 1 to it. So I will have a horizontal asymptote at y equals 2,000, because 2,000 divided by 1 is 2,000. And so what does that mean in context? that is the max, the max number of mice on this island. Okay. According to this model, what is the maximum sustainable population of mice that will inhabit this island? Well, that's actually what we just answered. I'm not sure why there's two different, essentially the same thing. Okay. According to this model, how many months will it take for the island to be inhabited by 15 mice? Okay, so now I know that the output, the total number of mice, will be 1,500. And now I'm going to use this equation to determine how long it will get there. So I have 1 plus 20 to the e to the negative 0.1 times t, or x. So how much time? I want to know how many months, and t is in months. Okay. All right, so I got to find t. I got to get t by itself. So I have a fraction. How do I get the fraction? How do I eliminate the fraction? I'm going to multiply both sides by the common denominator. And so I'm going to multiply both sides by 1 plus 20 times e to the negative 0.1 times t. Okay, I'm going to multiply that side by that, and I'm going to multiply the right-hand side by that. And this will cancel on the right-hand side, and that will leave me with, on the left, 1,500 times 1 plus 20 times e to the negative 0.1 times t, which will equal 2,000. Okay. Again, I'm trying to get the value of t. I'm trying to find t. And so I need to then move, I'm going to then divide by 1,500 on both sides. 1 plus 20 e to the negative 0.1 equals 2,000 divided by 1,500, which is essentially the same as, you could replace that with 4/3. And I will then need to subtract 1 from both sides. Okay, so I'm going to subtract 1 from both sides. 20 times e to the negative 0.1 times t, which is equal to 4/3 minus 1, which is 4/3 minus 3/3, which is the same as hold on one second. Let me confirm my work. Okay, I'm sorry, I lost my train of thought. 4/3 minus 1 is the same as 4/3 minus 3/3, which is 1/3. I now need to divide both sides by 20. I get e to the minus 0.1 times t, which is equal to 1/3. I have to divide by 20 again, which is this 1/60. Okay, how do I get rid of the exponent? I am going to take the natural log of both sides, and I get negative 0.1 times t is equal to the natural log of 1/60. I then divide both sides by negative 0.1, and I find t to be equal to the natural log of 1/60 divided by 0.1, and I will find that t to be 40.94. And now we got to go make sure we know the units, and t was given in months, and so this is the number of months. Okay, we have a conservation organization releases 25 Florida panthers into a game preserve. They believe that the number of panthers in this game preserve can be modeled by this function that's given, and they where t is the number of years since the panthers were released. Okay, so it's given by that function there, and says, what is the horizontal asymptote for this function and the context, and what is the significance of this? Okay, so basically, if I want to know the horizontal asymptote, I'm going to determine what happens to this function as t approaches infinity. And so essentially, if I take e to the negative infinity, that is the same as 1 over e to the positive infinity. And so this portion of that equation goes to 0, and I get 200 divided by 1. And so the horizontal asymptote is located at y equals 200. And what is that in context? This essentially is the amount of panthers that this preserve can support. So this game preserve can support a maximum population of 200 panthers, because eventually maybe the food supply is gone, or maybe the well, that's probably what it is actually, but anyway, okay. According to this model, how many years will it take for the game preserve to be home of 120 panthers? Okay, so now I have 120 has to equal 200 divided by 1 plus 7 times e to the minus 0.25 times t. And they want to know how many years, and t was the number of years. So we got to find t. How do I get rid of this fraction? I'm going to multiply times the common denominator. So I'm going to multiply both sides by 1 plus 7 times e to the minus 0.25 times t. And I will get on the left-hand side 120 times 1 plus 7 e to the negative 0.25 times t is equal to, and on the right, I will have 200. I will divide both sides by 120. And I will get 200 over 120, which is the same as 5/3. I will then subtract 1 from both sides, and I will get 7 times e to the minus 0.25 times t, which will equal 5/3 minus 1, which is the same as subtracting 3 over 3, which will be equal to 2/3. And then I will need to, so what do I have now? I have 7. I got to get rid of 7. I got to divide this side by 7. I got to divide by 7 on the right-hand side, which is the same as multiplying by 1 over 7. And I will get e to the negative 0.25 times t is equal to 2 over 21. How do I get rid of the exponent? I will, in this case, take the natural log, and I will get on the left-hand side, negative 0.25 times t is equal to the natural log of 2 over 21. And then I will divide both sides by negative 0.25, natural log of 2 over 21 divided by negative 0.25. And that will equal, plug that into your calculator, and I get 9.406. And we need to confirm what the t is the number of years. So that's why I know the units are years. There we go. All right, try one yourself. Welcome back. This is the number of smartphones that are sold globally can be modeled by this function where t represents the number of years since 2000 and nt is in millions of smartphones. Graph the function on your calculator and describe the shape in context of the problem. So you can go and plug that in. In fact, let me do that quick and I'll tell you what my windows are. So you should definitely be practicing this. Okay, so I plug this into my calculator. I have top left on my calculator, y equals, and I typed this in to my equation. And instead of t, I used x. So this will be x. And where do I find the x on that calculator? That is the button that is x comma t theta n, which is to the right of your alpha key. And so that's how you get x in there. Make sure you're using the negative, not the minus symbol. Make sure that you are putting this in parentheses, and you also need to make sure your stat plots are off. And so once I have that in my calculator, I then have to go to window, and I'm going to make some good choices here. So I know that my maximum value for y is going to be 1600. So I knew that y max was going to be 1600. I kind of wanted to start at, you know, I put my scale at, I think I had my y scale at 500. So I made those choices. Then I kind of had to mess around with my X value. So I had my X minimum at 0. And then this took me a few iterations to find my maximum value so that I had a graph that I liked, and I picked 50. And then I had my scale, my X scale at 5. Okay. And then once I did that, I was able to kind of have my graph show up. It was kind of more looking like this. And I had a nice graph view. Okay. All right. So now we've graphed it, and we want to describe its shape in context of the problem. So what do we know? We know initially, I'm going to run out of room. Initially, the number of smartphones sold sold globally increased at an exponential rate. I'll just, okay. It eventually, or the rate eventually peaked. The growth rate peaked and then began to slow down. Where did that happen? That happened at that inflection point. Okay. Eventually, the growth rate, eventually, let's see, as the number reaches what? 1,600 million, which is the same as 1.6 billion. As it reaches 1.6 billion, the growth becomes very small, if essentially 0. Okay. All right. This model has a horizontal asymptote. What is it? Explain its significance. So how do you find that horizontal asymptote? You find what happens to that function as the time goes to infinity. And so you essentially end up with 1 plus 0. And where did I get that 0? E to the negative infinity. So you plug in infinity for time. And what is e to the negative infinity? That's the same as 1 e to infinity. And if that becomes 0, and so that is where that goes. And so now we have 1,600 divided by 0. So y equals 1,600. There's your asymptote. What does that mean? That is the max number of smartphones sold. Max number of smartphones sold. Okay. Sold globally. Doesn't say per year, even though he said per year. But anyway, that's what that number means. Okay, will be, what is the number? Be 1,600 million, which is where the 1.6 billion comes from. Okay. According to this model, you didn't have to convert that. I'm just telling you what that is. All right. According to this model, in what year were 1,500 million smartphones sold globally? All right. In what year? Okay, I was going to have 1,500 million, and I have 1,600 divided by 1 plus 2,700 e to the minus 0.65 t. And I'm looking for t. I have to get rid of this fraction. What do? I multiply by the common denominator on both sides. And so I will multiply both sides times 1 plus 2,700 times e to the minus 0.65 times t. And I will have that fraction cancel on the right-hand side. I need to then divide both sides by 1,500. And I will get 1 plus 2,700 times e to the 0.65. T is equal to 16 divided by 15. I then need to subtract 1 from both sides, and I get 2,700 times e to the minus 0.65 t is equal to 16 over 15 minus 1, which is 15 over 15. which will be 1/15. Okay, I now need to divide both sides by 2,700, which is the same as multiplying times the reciprocal. So I'm going to multiply both sides by 0.1/2,700. On the left-hand side, I am left with e to the minus 0.65t. And on the right-hand side, I get 1 times or 1/15 times 2,700, which is the same as 1/40,500. How do I undo the exponent? In this case, I take the natural log. And on the left-hand side, I'm left with negative 0.65 times t. And I have the natural log of 1/40,500. Divide both sides by negative 0.65, and you will get t is equal to the natural log of 1/40,500, all divided by negative 0.65, and that will give you t to be equal to 16.3. Be careful, what was the question? In what year did this occur? Okay, so we're getting pretty close to 15 to that maximum 1,600 million. So this occurred, let's see, when did this start? This started since year 2000. Yep, so this has started in year 2000 based on the problem. So I've got to take year 2000 and I need to add 16.3, and I will find that to be year 2016. So what year? 2016. That is approximately where we have reached this. We're getting pretty close. So that wasn't that long ago where we have kind of now a different model. We have a product launch that no longer is growing. It's now into replacement because the majority of people in the world have a smartphone. So anyway, that's a kind of a cool example to this particular math problem. So hope that lesson made sense. This is logistic growth model and how to apply it to real life data. So reach out to me if you have any questions.